Morning everyone, welcome back to science class. Today we are going to cover topic 6.3, measurement of forces, and topic 6.4, calculating work done. Before we get into it, let's do a recap of our previous lesson, which was 6.2, effects of forces. So our step to success before was to state the 4 effects of forces on a body at rest and in motion. And secondly was to state the changes produced when a force is applied onto the body at rest or in motion. So what are the 4 effects of forces on a body at rest? Firstly, it's changing in speed. You can change the direction of a body. You can change the size of the body and change the shape of the body at rest and in motion. Secondly, what are the changes that are produced when a force is applied? So firstly, when an object is moving, when a force is applied in the same direction as motion, then the object can move much more faster. Secondly, when an object is moving, but the force applied is in the opposite direction as motion, then the object moves much more slower. Next, if the force is applied in a different direction, then this will cause the moving object to change the direction of motion. The size of an object can also be changed by applying force. For example, when you blow a balloon and this pushes air into the balloon, therefore increasing the size of the balloon. A force can also change the shape of an object. For example, if you apply force to a plasticine, it can change its shape. Now let's focus on our learning objectives of today. 6.3, measurement of forces. We're going to cover measure force using a spring balance and state that Newton is the SI unit for force. 6.4 is about calculating work done. So our learning objective is to define work done as the product of the force and the distance moved in the direction of the force. We need to calculate work done using the equation work done equals to force times distance moved and state that joule is the unit of work done. So our step to success today is firstly to state the apparatus used to measure a force. Second, state the SI unit of force. Third, define work done. Fourth, calculate work done. And fifth, state the unit of work done. So the SI unit of force, remember that SI unit is the standardized unit. For example, for mass, it's in kilograms. For distance, it's in meter. And for force, the SI unit for forces are actually measured with the unit Newton, which is a capital letter N. So make sure that you don't draw a small letter N. So how do we measure forces? Forces can be measured by an instrument called the spring balance, and they usually can look something similar to this or something like this. This is the kind of more like traditional spring balance where there's literally a spring there. There's also a spring here. This one is similar to like a weighing scale that you have, and I have a feeling this is also called like something like a compression balance, but let me just check the book really quickly. Yeah, that's right. So for the bathroom scale, it is also called a compression balance, and something like this where you find like this in the kitchen, this can be called a spring balance, but it is also called a compression balance because you compress, it compresses the spring instead of like the spring like pulling down just like this. Alright, so how does the spring balance work? So the spring balance itself, it looks like this, and it has like a hook at the bottom, and you can add like the load on it, so you can measure the force of that load itself. And when we're talking about the force here, we're looking at weight, and weight is actually the weight of an object if you have a look over here, is the mass of an object times acceleration of gravity. And weight itself is a force. But however, mass, so when we're talking about your mass, it is not a force unless you have gravity acting on it. So when we're looking at the weight of an object, which is the force of gravity acting on that mass of the object, we get m, which is the mass of the object, usually in kilograms or grams, and then you times it with gravity, acceleration of gravity. Acceleration of gravity is usually 10 meter per second square, and this is usually pretty constant. So whenever you're looking for the weight of an object, which is the force, you get the mass in kilograms and then you times it by 10. So how does this spring balance work is the fact that the spring itself, it has a steel spring in the middle, and then it has this hook that is attached to it. So what you can do is that you can add the load here, and that load will actually get that spring to stretch down. So because of the force of gravity, it's pulling the spring downwards, and you can see the dial over there, and it moves. So whenever it stops moving, that would be the force that you're looking for. So make sure that when you are measuring, make sure you're looking at that line over there and see where it stops. So over here, so we're just gonna watch this video a little bit. Okay, so usually it starts at 0, so make sure that when you're using this, you can calibrate it, which means that sometimes the spring, this one, the starting point might be like below, so make sure you can change it to 0 first. This happens as well with bathroom scale sometimes. Like if it's not the digital one, you have to pretty much scale it up, calibrate it back to 0. Okay, so once it's at 0, then you can start to get a load on it. So how does the spring balance work is that gravitational forces will pull the spring in a downward direction. But however, the spring itself has a force, and the fact that when we talk about spring, it springs back. So the spring is going to pull the load in the opposite direction. So it's going to be the opposite way. And this load is going to keep on moving and moving down, and it's only going to stop and become stationary when the force of gravity is equal to the force of that spring moving up in the opposite direction. So when it stops, so this is the weight of that load. And you can see over here, so you have grams and in newtons, right? So Newton is a force, and then gram is the mass. So you can see over here that the mass is 28 grams, but the force here is 14. So Newton and in grams. So you can see that it's different. When we're talking about mass versus weight, they are actually different things. So if you want to watch this video, you can go onto this link right here, youtube.com/ okay, this link basically, I'm going to link it down in the description box below, and you can watch this whole video. It's much better of an explanation than when I explained it, honestly, but I tried to explain it as simple as I can. All right, so let's move on. Now we're going to talk about work and a little bit of energy, work done basically. So whenever a force is applied onto an object, causing the object to move in the direction of that force, work is done by that force. If a force is applied but the object doesn't move, then no work is done. Basically, it's kind of saying like, so if you have a look at this like picture over here, you have this man, and this person right here is trying to lift this box, right? And this is not budging. However, over here, this person can lift the box up in the direction. So the force is moving upwards. right? It's moving upwards. So there is a distance that is moved by this object. So it's from the ground and moved up. However, this one is not moving at all. So what we say over here is the fact that work is only done when an object moves with a force exerted on it. So for work to be done, firstly, there is a force acting on the object. So the person is maybe lifting it up or pushing it to the side, but this person's trying to lift it but couldn't. Okay, secondly, the object needs to move. The object is not moving, then work is not done. But here the object is moving, that means that work is done. And thirdly, the movement of the object is in the direction of the force. So here the force is lifting upwards, and you can see that the box is moving, so from the ground and upwards as well. So here work is done. But here, trying to lift that object, but it's not moving at all, so we say no work is done here. And here we have work done. So overall, work done has to have a force acting that object, and the object has to move, and the movement of the object must be in the direction of that force. So how do we define work done actually? Sorry guys, my battery was about to die. Okay, I'm back. All right, definition of work done. Work done is the product of the force and the distance moved in the direction of the force. How you can actually remember this definition is if you can remember the formula for work done. So I'm going to say this one more time, that work done is the product of the force and the distance moved in the direction of the force. So calculating work done, you can use this formula. Work done equals to force times distance moved in the direction of the force. So this actually is pretty much the definition. So remember, work done is the product of a force and the distance moved in the direction of the force. So let's get back. That's right. So it is pretty much basically the formula, but you make it into words. So that is the basic definition. So if you can remember this formula right here, then you are good to go. Okay, so for work done, force and distance moved, we also need to have the proper units for it. Work done, the SI unit for work done is in joules, which is a capital J. Force, remember, it's in Newton with a capital N, and for distance moved, it has to be in meter. So that's a small letter M. So make sure that all your units have to be in this form, and then you can actually use this formula. Work done in joules, force in Newton, you times it by distance moved in the direction of the force, which is in meter. You can also try to remember work done by using this formula triangle. So you just draw a triangle and you divide it into 3. So at the top right there is W for work done. Force is at the bottom right next to distance. So this triangle kind of shows you the fact that anything that is below the top triangle, that is divide. And then if they're next to each other side to side, so that's times. So I'm going to show you guys how you can actually use this formula triangle. Right, so we have a problem right here. So usually, I guess an exercise, a question. Yes, so question 1. How much work is done when a weight of 12 Newton is raised vertically through 50 centimeter? Okay, so firstly, we have a question asking us about work done. To calculate work done, we have weight in 12 Newton. So Newton, remember, that is a force already. So this is the force we're talking about. And it is raised vertically through 50 centimeters. So that is the distance that we're talking about. So if I draw this, it'll look something like this. So you have a box that's 12 Newton. So that is the weight of that object. And you're trying to lift it up and lift it vertically by 50 centimeters. So what we're looking for here is work done. So how do we calculate work done? You can use this triangle to remember. So if you draw this triangle, you put W at the top, force at the side, and distance at the other side. So since we're looking for W, so what you can do is that you can either circle this, or you can put your thumb or your finger on it, and what is left here is F next to D. So remember, when they are next to each other, you times them. Also, make sure to remember that the unit of work done is in joules, force is in Newton, and distance is always in meter. So now we have our formula over here. Because we're focusing on W, that means we're looking at here, right next to each other. So W, work done, is equals to force times distance. And the force here is found in the question, which is 12 newtons, times the distance that is mentioned here is 50 centimeter. However, remember that distance has to be in meter, so we have to convert centimeter into meter. So what we do is that we divide it by 100. So we get 12 Newton times by 0.5 meter. Now finally we can multiply them. So the product will be 6 joules. Alright, next. So I've already highlighted this for you guys. If 360 joules of work are needed to move a crate at a distance of 4 meters, what is the weight of that crate? So what we're looking here is weight, and remember, weight is the force of gravity acting on that object. So weight is the force, so we're going to cover force here, and what's left is W and D. And remember that when they are on top of each other like this, that means it is divide. So recall the fact that work done has to be in joules, force is in Newton, and distance is always in meter. And we have that there and there, so we don't need to convert anything anymore. So what is the formula? So F right here is here divided by this one. So force is equals to work done divided by distance. So make sure you're writing down this formula, because when you write down the working, you actually get marks for that as well in your exam. All right, so it's equals to, so what is your work done? So your work is 360 joules, and you're going to divide it by the distance, which is 4 meters. If you have your calculator with you, you can do this with me. So the force would be equals to 90 newtons. Okay, next. So if 68 joules of work is necessary to move a 4 Newton crate, how far will the crate move? So here we are looking for distance. So if we circle this, what's left is we get work done and force. And remember that this is right below the line. That means we have to divide. And remember, work done is always in joules, force is always in Newton, and distance is always in meter. So the formula we're writing here is D for distance is equals to work done divided by force. And over here, work done is 68 joules, so we don't need to convert anything there. 68 joules divided by 4 Newton. And just use your calculator, and you're going to get 17 meter, because distance is in meter. And that is how we can use this triangle and the formula to calculate work done, but also force and distance that is involved in it. All right, so thank you for sticking with me, and now we're going to go back to S2S, our step to success. So what is the apparatus that is used to measure the force? We needed to talk about the SI unit of force. Defining work done, we calculated work done and state that work done, what is the unit of work done? Okay, so the apparatus used to measure force is the spring balance. And the SI unit of force is in Newton, which is the capital letter N. How do we define work done? Work done is the product of the force and the distance moved in the direction of the force. And calculating work done can be used with this formula. Work done is equals to force times distance moved in the direction of the force. Remember that the SI unit for work done is in joules, force is in Newton, and SI unit for distance is in meter. So if you get a question that gives you in centimeters, then you have to convert that into meters. You can also calculate work done using this right here, this triangle. What is the unit of work done? So work done is in joules, which is a capital J. All right, so that is the end of today. I hope that you guys find this lesson not too difficult, and please stay safe and healthy. I'll see you guys next time.